In this third part of the discussion of the main research going on in the Dependable Computing Systems Lab, we are going to look at thrust number 3, which is based on dependable embedded wireless networks and what we can do to enable these small embedded devices and systems that are built out of these small embedded devices to be still dependable. One buzzword that you may hear in this context is called Internet of Things. So these are really small scale devices which are embedded in our physical spaces. The cameras sensing different parts, different aspects of our physical environment, such as temperature or pressure or humidity or sound level and so on. And being able to analyze this kind of sensory information and being able to take certain response actions, certain actuation actions in response to what is being sensed. Now, in order to build a dependable system out of these kinds of devices, oftentimes these are small form factor or low-cost devices, and they're always placed in sort of uncertain or hostile environments. And they have constraints, sometimes fairly strict constraints on various resources, such as the amount of energy resource that they have available. You don't want them to run out of energy battery too often so that you have to go and replace these energy resources. The amount of wireless bandwidth that they can use. Because they're sometimes in physically insecure environments, the nodes are even open to physical tampering. And these networks operate for extended periods of time in disconnected mode of operation. So they're not always connected to a central computer. So our goal is to provide a set of middleware softwares which will enable somebody to build a dependable system out of these kinds of devices. And once you have set up the system, our middleware should be able to provide you with detection when something goes wrong, diagnosis to be able to pinpoint what went wrong, and here the possible causes are really vast. This could be in the digital domain or even in the physical domain. For example, a snowstorm came about and that completely changed the wireless characteristics of the transmission or the reception of these devices. But as these devices are now being used in more and more critical, safety critical, security critical environments like smart buildings, like monitoring industrial control systems, it is important to be able to build dependable systems out of these inherently unreliable, failure-prone components. So one solution direction we are investigating here is, if you take a look at these devices, they basically execute code as root throughout. And we want to do the least privilege and randomization based security. So allow just the limited part of the code that requires elevated privilege and exactly what kind of elevated privilege it needs. And through compile time mechanisms, insert in the mechanism to elevate privilege and then de-escalate privilege right after that code executes. Then you randomize the binary so that an adversary cannot go off, reverse engineer this binary, and craft sophisticated attacks against our embedded systems. And place canaries strategically in the control and the data regions in the memory so that these kinds of memory corruption attacks can be easily detected and flagged. And this is joint work with Matthias Bayer, a faculty colleague at Purdue. Another thrust in this space, another project in this thrust is game theoretic security. Typically in your embedded systems, you have many assets. Sometimes these assets even belong to different stakeholders. So for example, in an energy delivery system, you can have the energy producers being one stakeholder. The owners of the pipelines through which energy is transmitted is another stakeholder. The utility providers are another stakeholder, and so on. So in these kinds of cyber physical systems, you have many assets, and it's not possible to secure all the assets to the same level. So you have to make strategic and pragmatic decisions about which assets to secure. And we are bringing to the table game theory to be able to decide what kinds of assets, which assets, and to what level should they be secure. We also answer the question that since there are interdependencies among the various stakeholders, how should these stakeholders, the defenders, the good guys, how should they collaborate in order to secure the assets? It's possible that if I secure my asset, you are going to benefit from it. It's also possible that by both of us contributing to some shared resource, like a shared software that both of us use, we would be able to make both of our systems secure. But importantly, you have to make these decisions in a rigorous, quantifiable manner. So in this schematic, you're seeing an industrial control system, two different industrial control systems with some shared resource, such as the RTU is a shared resource which is between these two industrial control systems. And you can use attack graphs to map out how attacks can impact these different cyber-physical systems. And in our analysis, we evaluate various kinds of defensive strategies. So for example, one defensive strategy, the green curve, is where each stakeholder, each defender makes her independent decision about allocating the defense budget. The red curve is where there is a joint defense mechanism where the stakeholders collaborate, but still the decision is distributed. And then the blue curve corresponds to the ideal, the social optimum, where there is a centralized entity which takes information, has complete information from all of the stakeholders and computes what's going to be the best defense scenario. And we see that, of course, the blue curve is the best. The y-axis is the expected loss, so the lower that is, the better it is. Of course, the blue curve is the best, but depending upon how many assets there are, how much defense budget each player has, the trade-offs are, the difference is going to change. A third direction within this trust is record and replay. So what we want to achieve is that as these devices are deployed in the field, we want to record just the right level of information that will allow us to troubleshoot if something goes wrong. So of course we would want to record absolutely every piece of information that's going on, that's being perceived at that node. But that's going to be too expensive. It's going to be too expensive in terms of the amount of storage that we'll need. It's also going to be too expensive in terms of the amount of time you will spend in doing all that recording. So ideally, what we would want to do now is to record just those sources of non-determinism. So when you bring this node or trace back into the lab, you won't be able to recreate it without those sources of non-determinism, like a sensed value, like an interrupt coming in, which is changing the code path. So our solution has been to record just the right level of information and then compress this level of information so that you can actually save a lot of it on your device. And this has the flavor of an airplane black box. So you keep recording these events, compressing them and storing them in a black box kind of a scenario where you have a circular buffer. So something that was recorded 30 minutes back is going to be overridden. So the holy grail here, which we've been able to achieve for certain kinds of embedded devices, is when you bring this device back into the lab, or when you can bring the trace back into the lab, the device is still embedded in the physical space. Using the trace and what we have recorded, you can replay exactly what went on in the field. So we have a pure hardware solution, hardware firmware solution called Aveksha, and then a pure software solution called TARDIS, where the software solution basically inserts some LLVM passes in order to do the data logging and the data compression. And the logging and compression are done opportunistically when there is some slack in the timing of the regular application. So if you're interested and want to learn more, please check out the website of our group, the Dependable Computing Systems Lab. Check out the software that we put out through the GitHub page, and you're always welcome to stop by our labs or my office here at Purdue University. The work that I have described here has been generously funded by a variety of federal and state government and private sources. Goodbye.